Welcome back. It's the start of our last unit before we get ready for our final exam. Hopefully you're excited and finding some relief in that. This last unit we're going to look at exponential equations and functions, and then logarithms and how the items are connected, okay? So we're going to start with exponential equations. Now what does it mean for an equation to be exponential? Some of you may be thinking, well, it has an exponent, which is a reasonable thought, but if we were looking at something like x squared plus 3x plus 2 equals 0, that's an equation, but it's not exponential, right? It has an exponent, but that doesn't make it exponential. We know this because we've seen a lot of these. This is a quadratic equation. So what is it that's going to make an equation exponential? Is not just that it has an exponent, but the exponent is your variable. So this is an example of an exponential equation where the exponent is a variable. Okay, so an exponential equation, let's go to blue here, an equation is exponential if the variable in the equation is the exponent. All right, so for example, again, 3 to the x power equals 9 is an exponential equation. And I would argue here that I should not have to teach you anything for you to be able to tell me the solution to that equation. 3 to what power is going to be 9? We should all be able to look at this and say that the power of 3 that makes 9 is 2, and so x has to equal 2 in that equation. Well, clearly the exponential equations we're going to be solving wouldn't all be that simple, or I wouldn't have to teach you anything here. But the concept that we're technically using here is a concept that we will use to solve exponential equations that are a little more challenging. The reason we can do this so easily is because we know that 9 is 3 squared. So instead of thinking about this equation as 3 to the x power equals 9, we're going to think about this as 3 to the x power equals 3 to the second power, where we can think about the 9 as 3 squared instead of 9. So it's rewritten, right? Rewritten so that we have common bases here. Because once these bases are equal, the exponents have to be equal as well. So once we get the bases to be the same, we're not worried about those. We're going to be solving with our exponent. So there it is, x equals 2. Okay, so then if we have something a little more complicated, let's say we had, not 4, let's say we had something like 16 to the x power equals 64. Well, there isn't an exact power of 16 that makes 64. So what we want to do is find a common base, okay? Now before I show you how to do this and how to do the ones that, again, they're going to be a little more challenging, we're going to fill in this little table, and it's just going to be like a little reference sheet. Some of these numbers we should know, but knowing various powers is going to be helpful in the process of solving that we're going to be looking at today, and actually we'll go back to this question in just a minute, okay? So let's fill in this little table first. We have a base, and then, so our base here is 2. I want to know 2 squared is going to be 4. That's what I want to put here. 2 cubed, 2 to the power of 3 would be 8. 2 to the 4th power would be 16. 2 to the 5th power is going to be 32. To the 6th power would be 64. To the 7th power would be 128. To the 8th power would be 256. 3 to the power of 2. 3 squared is going to make 9. 3 cubed is 27. I'm hoping we knew those. And then 3 to the 4th power is 81. 4 squared is 16. 4 cubed is 64. 4 to the 4th is going to be 256. And then I'm just going to, oops, for some reason I skipped this, is 243 here, 3 to the 5th power. I'm going to pause here for a second. So I'm going to come back to this second equation we were looking at here. 16 to the x power equals 64. If I can find a base that these numbers have in common, then I want to try to rewrite these with that base they have in common. So I found a row here that has the numbers 16 and 64. Oops, went a little too far. I found a row here that has the numbers 16 and 64. So 16 and 64 are both powers of 4. That means they have that base of 4 in common. So instead of writing the 6 or leaving the 16 as 16, I could rewrite the 16 as 4 squared, and then I still have that power of x there. And then 64, again, also a power of 4. 64 is 4 to the 3rd power. So instead of 64, I can make this 4 cubed. And then just like I had over here, once the bases are equal, they're going to cancel. So the 4s are the same, that means the exponents have to be the same. So the exponent here, which is a 2x, has to equal the exponent here, which is a 3. Then dividing by 2 tells me that the solution here is going to be 3/2. Okay, so that's sort of the goal. I know that was maybe a little much for right now, but that's the goal, is to be able to find some common bases. So now that I did all that, I don't want to mess up my table, so I'm going to undo a million times. And almost there. Oh, sorry, I just wanted to get rid of that highlight without messing up my table. Okay, so let me get rid of this. Okay, and let's keep filling in this table because these are going to be handy numbers for us to reference. Now, some of these we should know, so a lot of the problems that we see, we should be able to identify the common base, but maybe you're looking at 243 and not recognizing that it's a power of 3, or maybe you're looking at 256 and not recognizing that it's a power of 4, okay? So let's finish this table up, and then we'll talk about some steps, and we'll try this out a few more times. So 5 squared is 25, 5 cubed is 125, and then 5 to the 4th is 625. 6 squared is 36, 6 cubed is 216, and 6 to the 4th power, I do not know. 6 to the 4th power is 1,296. And all these areas that are grayed out here, they're just grayed out because, not that those powers don't exist, but they're not numbers that we encounter a lot. So what I'm filling into the table here are the ones that we would likely see. I don't even know that we would see 1,296 in a problem, but we definitely won't see any of these things that are grayed out. Okay, 7 squared is 49, 7 cubed is 343, 8 squared is 64, 8 cubed is 512, 9 squared is 81, 9 cubed is 729, 10 squared is 100, 10 cubed is 1,000, excuse me, 11 squared is 121, 11 cubed is 1,331, 12 squared is 144, and cubed is 1,728, 13 squared is 169, 14 squared is 196, and then 15 squared is 225. Now, it's possible that you see something that doesn't occur in this table, but I think the majority of the problems that we're going to encounter can be handled with one of these numbers, so hopefully this will come in handy. Now, the steps, right? How do we use this table? We're going to use this table and try to find these numbers in terms of what the base of those numbers is. What base to what power gets those numbers, okay? So we're going to look for a common base using that table. And we're going to rewrite each side of our equation as a power of that common base. The goal is to get both sides to have the same base, because once the bases are equal, the exponents have to be equal too. So once the bases are equal, they can cancel, and we can set the exponents equal to each other and solve there. And then the good news here is we can always check our answers by plugging them back in. So it's kind of nice with an equation. We plug the answer back in and make sure that it actually works. Okay, so let's try this out here. So 3 to the 2x power equals 27. We're looking for a common base there. I'm hoping we know that these are both powers of 3, that 3 is 3 to the 1st power, and that 27 is 3 to the 3rd power. So since this side is already written as a power of 3, I'm going to leave it alone. This side I'm going to rewrite as, instead of 27, 27 is 3 to the 3rd power. All right, now I have common bases. If those bases are equal, the exponents have to be equal. So our bases now can cancel, and we can solve with just our exponents. So the 2x here has to equal the 3 that's here. So if 2x has to equal 3, then x has to equal 3/2. Pretty simple. Okay, and we can plug it in to check it. So we have 3 raised to the 2 times, oops, let's keep all that together. 2 times, come on cursor, times 3/2 power, and that does in fact get us 27. Okay, so we can verify with our calculator. All right, let's try that again. So 125 and 25. Again, I'm hoping that we're recognizing. If not, we go to our other page and we look for 25 and 125. Well, 25 and 125 both happen in this row, which means we can rewrite the 25 and 125 as powers of 5. 25 becomes 5 to the second power, 125 becomes 5 to the third power. Okay, so now we're going to go back here, and let's see. Instead of leaving this 125 to the x, the 125 becomes 5 cubed. Same thing, right? So I'm replacing 125 with 5 cubed, and I can't forget about my x. That's got to stay there. And then on the other side, 5 squared makes 25, so 25 becomes 5 to the second power. Now this is our power rule here. These exponents get multiplied, so I could really just say this is 5 to the 3x equals 5 to the second, but our bases are equal. If the bases are equal, the exponents have to be equal. So we're going to cancel out those common bases and solve with just the exponents. So the 3x here has to equal the 2 that's here. And if 3x has to equal 2, then x has to equal 2/3. And again, if you wanted, you don't do this every time, but if you want to check your answer, let's put in 125, and let's raise it to the 2/3 power. I swear I typed in a 2. 2/3 power, and there it is, 25. Okay, so all can be verified. And here's one for you to try. Feel free to pause the video. You actually have a couple of options on this one. Otherwise, 16 and 256. Let me go to the other table here. If I was looking for 16 and 256, I have a couple of options. 16 and 256 both happen in this row, and they both happen in this row, so you could use either base there. You could either make the 16 2 to the 4th and the 256 2 to the 8th, or you could make 16 4 squared and 256 4 to the 4th. Okay, so you have the option. Either one's going to work. So let me go back here. Not you, calculator. I'm going to use powers of 4. So the 16 is 4 to the second power, and I'm going to bring down the 3x. And then the 256 becomes 4 to the 4th power. These exponents get multiplied, so this is really 4 to the 6x power here, equal to 4 to the 4th. And now those bases are equal, so our bases can cancel. So the 6x has to equal the 4. If we divide both sides by 6, we get 4/6 as an answer, but that reduces. So again, an answer of 2/3. Okay, not too terrible. All right, 4 and 32. 4 and 32. Let me go back to my table. 4 and 32 are happening here. 4 we could say is 2 squared. 32 we can say is 2 to the 5th. So back here, we're going to rewrite the 4 as 2 squared, and make sure we bring down our x plus 2, and then the 32 becomes 2 to the 5th. Okay, so now we have common bases. Now let me get rid of these parentheses first. Again, we have to multiply our exponents here, power to a power. So this is going to be 2x and then plus 4. We have to make sure if there are multiple terms in that power that we distribute. That's a common mistake I see on this one. So make sure you distribute. So we're looking at, again, 2, let me fix this. This is 2 to the 2x plus 4 power equal to 2 to the 5th. But now again, our common bases are going to cancel. So the 2x plus 4 has to equal 5. We're going to subtract the 4 over, so that 2x is equal to 1. And that means x has to equal a half. X has to equal 1/2. And if you wanted to check, again, don't need to check every time, but if you're just unsure, right, put it in the calculator. So 4 raised to the, in parentheses, I'm putting in a half, and then I'm adding 2, and when I hit, oh, there it is, 32. I was going to say hit equal, but it automatically does it. So we can verify that our 1/2 is correct. Okay. 49 and 343. Maybe you don't recognize the 343, but you should definitely recognize the 49, and that should be telling you that these have to both be powers of 7. So 49, that is the same as 7 squared, and let's bring down the x minus 1. 343, that's 7 cubed, and let's bring down the x plus 2. Now let's distribute, right? It's going to be 2x minus 2 here, and 3x plus 6 here. So we have 7 to the 2x minus 2, and 7 to the 3x plus 6. But now we have common bases. So we can cancel out those common bases and make our exponents equal. So 2x minus 2 has to equal 3x plus 6. Let's get those x's together. And you can move whichever one you want. I'm just going to choose the 2x's. So negative 2 is equal to x plus 6. And now I can subtract over the 6. And that means we have x equal to negative 8 for our answer. Okay, now this one, since we have variables on both sides, we'd have to check both sides. So 49 raised to the, we're plugging in a negative 8 minus 1. And that gets us that ridiculous looking answer there, but the other side better be the same. So the other side, I put in 343 raised to the, raised to the negative 8 plus 2. Plus 2, and there it is. Same ridiculous looking number. Now, the calculator is giving you scientific notation there, and that's because the decimal is really, 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 really small. So think about if you had 343 and you're raising it to the negative 6th power. Remember, that's 1 over 343 to the positive 6th power. That's a really small decimal. Okay? So don't freak out about that scientific notation. All right, let's see. Another one for you to try. Feel free to pause the video. Otherwise, hopefully you're recognizing these are 8 and 16 are both powers of 2. 8 is the same thing as 2 cubed. And then we bring down our 2x. And then 16 is the same as 2 to the 4th power. And then we bring down our x minus 4. So we have a 6x here and a 4x minus 16 here. So this is 2 to the 6x. 2 to the 4x minus 16. Now we can cancel out those common bases. So we have 6x equal to 4x minus 16. I want to get the x's together, so I'm going to subtract these over. Now I'm left with 2x equal to negative 16. And now if I divide, I get, coincidentally, the same answer I got on the last one. So x is equal to negative 8 once again. All right, hopefully you're feeling pretty good about this so far. So number 5 is a little tricky because we have common bases, but they're not on the same side of the fraction. So we have 6 to the 1st power here, and I know that 36 is the same as 6 squared. So we see the common base, but if I have 1 over 6 to the 1 here and 6 to the 2 here, I can't just cancel these when they're not on the same side of the fraction. So what we're going to use is our negative exponent rule in reverse. Normally, we said if we have something with a negative exponent like 6 to the negative 1, we would move that 6 to the bottom and make the exponent positive. Well, now I need the 6 that's on the bottom of the fraction to go back to the top. So if I want to move the 6 to the other side of the fraction, I just have to change the sign of the exponent. So this, instead of 6 to the positive 1 on the bottom, becomes 6 to the negative 1 on the top of that fraction. And I'm going to bring down the x. And then 36 we know is 6 squared. So here, to change the side, or to change the side, how do I want to word this? If we want to change the side that the base of the exponent, side of the fraction the base of the exponent is on, we change the sign of the exponent. So changing the sign of the exponent allows us to move the base to the other side of the fraction. To move the base to the opposite side of the fraction. That is the negative exponent rule in reverse. Normally, if we start with a negative exponent and we move it to the other side of the fraction to make it positive, well, here we already have a positive exponent, but it's the same rule. If I move it to the other side of the fraction, I change the sign, okay? So here, we're going to multiply this and say this is 6 to the negative x equals 6 to the 2nd power. Now I can cancel these like bases. That means that negative x has to equal 2. Technically, we are dividing both sides by negative 1, and that tells me that x has to equal a negative 2. And again, that would make sense if we plugged it in, right? Let's put in, let's see, 1 over 6. And then if we raise that to the negative second, then we get 36. Because 1 over 6 to the negative 2, that's the same as 6 over 1 to the positive 2, which again is 36. Okay, let's try that again. So we have here 81 and 729. 81 and 729. If you don't know, let's go to the other side here. 81 and 729. Oh, what did I do? 7. Somehow I keep erasing stuff. 81 and 729 are both in this row, which means they're both powers of 9. So I'm going to rewrite them. Oh my goodness. Okay, so we're here. Now this is 1 over 9 squared. So 81 is 9 squared, and this is 9 cubed to the 2x plus 1. I can't cancel the bases yet because that 9 squared is on the wrong side of the fraction. So instead of 9 to the positive 2 on the bottom, we're going to make this 9 to the negative 2 on the top. And I'm just going to bring this down for a second here. Oops. Now that we have everything on the right side of the fraction, let's distribute and then we can cancel those bases. So we're looking at a negative 2x here and a 6x plus 3 here. So we have 9 to the negative 2x, 9 to the 6x plus 3, and now those common bases can cancel. So we have negative 2x equal to 6x plus 3. Gonna subtract the 6x over. That cancels. So now, running out of space, we're going to say negative 8x is equal to 3. And I can divide over that negative 8, making my final answer a fraction. That doesn't divide or reduce, so we're just going to say negative 3/8 is our answer. And if you wanted to check it, plug that negative 3/8 in on both sides, and you're going to see that it works. Okay? So here, hopefully we can see the common base again. These are going to be both powers of 10. So this is 1 over 10 cubed here. And then 100 is 10 squared here. Now this 10 cubed is on the wrong side of the fraction. So instead of leaving that as 10 cubed on the bottom, 10 to the positive 3 on the bottom, we're going to make it 10 to the negative 3 on the top. And now we can multiply our exponents. So that's a negative 3x here and a 6x here. So 10 to the negative 3x has to equal 10 to the positive 6x. Now our common bases can cancel. So we have negative 3x equal to 6x here. And sometimes these equations that have a little less tend to stump us. We are doing the same thing, getting our x's together. So I'm going to add these 3 over. That leaves me nothing on this side, and the number for nothing is 0. And then on the other side I have 9x. So if I have 0 equal to 9x, all I have left to do is divide the 9. Well, what's 0 divided by 9? It's still 0. So x equals 0 is our solution. And that would make perfect sense. Anything to the power of 0, do you remember that rule? Anything to the power of 0 is 1. So if I put a 0 here, I get a 1 on this side. If I put a 0 here, then 100 to the 0 makes a 1 on this side as well. So that answer makes sense to me. Alright, but again, if you want to use your calculator, you can plug it in. I got one last one. If you want to try it, feel free to pause. If not, let's see, 12 and 144 are powers of 12. This is 12 to the first here, and this is going to be 12 squared over here, right? But this 12 to the first is on the wrong side of the fraction. So I'm going to make this 12 to the negative first on the top, leaving the 4x, right? Instead of 12 to the first on the bottom, 12 to the negative first on the top. And on the other side, we're making this 144 12 squared and keeping our x minus 3. And then we're going to multiply. So that's a negative 4x here, and then 2x minus 6 over here. So we have 12 to the negative 4x equal to 12 to the 2x minus 6. Now our common bases can cancel, leaving us negative 4x equal to 2x minus 6. Let's get the x's together. If I subtract the 2x over, I'm left with negative 6x equal to negative 6. And now I can divide both sides by negative 6. And that tells me that x has to equal a positive 1. And again, just to verify, don't need to do it every time, but it is good to check your work, especially if you're unsure. If I have 1/12 on this side, and I raised it to the 4 times, oh, it's 1. 4 times 1, I get that decimal. Now on the other side, if I have 144 and I raise it to the 1 minus 3 power, I get that same crazy decimal. If I want the fraction, let's see, as a fraction, maybe it looks a little prettier. I don't know. Either way, both sides of the equation are equal when I plug the 1 in, which verifies that 1 is the correct solution. Okay, so this is the process we can use to solve some exponential equations. There will clearly be exponential equations that won't have common bases. For instance, like a 2 to the x power equals 5. There's not going to be a common base for 2 and 5. So we will be learning some other ways to solve. But for now, hopefully this one makes a little bit of sense.